Okay, we are at our final lesson in AP Chemistry. Wow. It's kind of random that it's the topic is nuclear, but at the end, I think it's kind of fitting in that it is, I guess, the smallest things to the biggest things, so it kind of covers everything. Anyway, let's do a little bit of review. We've discussed half-life before. You should know what isotopes are, but let's just go through what's going on here. If you're told Na24, like this, that is a particular isotope of sodium. And sodium has many isotopes. This means this sodium has a mass of 24, which means its protons plus its neutrons add up to 24. And in this case, it says the half-life is 15 hours. Of course, this is a contrived number. This is making it nice and easy for us. Question says, what percentage remains after 45 hours? Well, that's also really nice and contrived in that the fact that it's exactly 3 half-lives. So I know that because 45 divided by 15 is, of course, 3 half-lives. So that means the starting amount has been cut in half 3 times. So if you take 100% and cut it and cut it and cut it 3 times, first cut goes from 100 to 50%, then to 25, then to 12.5%. And that's how we get the answer, is how much of the original sodium 24 isotope remains. Now, then I want to look at this here. So radon 220. The top number is called the mass number because it describes the mass of the nucleus. We're ignoring electrons. Normally, we don't even factor in the mass of the electrons, but right now we're looking at the nucleus anyway, so there are no electrons in the nucleus. So that's the mass number on the top, so 220 in this case. The atomic number, 86, that tells you which atom you are, and it is equal to the number of protons. So in this case, reading this, we would say 86 protons. Assuming it's neutral, 86 electrons. And if you subtract 86 from 220, you get 134 neutrons. Now, what's interesting is that the periodic table does not show isotopes. It shows each element and its average mass of all the isotopes as we have encountered them so far. So I'm going to go to a site that I found recently that shows the isotopes. So this chart here, these are all the isotopes that are known. And every one of these little boxes, and they're tiny, every little box is a different isotope of all the different elements. And so, for example, you see right here, I'm at technetium. I can slide over, it's hard to stay on that element, but as I slide over, I go through all the different isotopes that are known. And we can zoom in on this and look at different isotopes and so on. But the thing I want to show you right now that's interesting is the black boxes are the stable ones, the ones that aren't radioactive or aren't likely to change. Notice down here, these ones, the angle of this graph, and the graph is the ratio of, let's see, it's going to be protons versus neutrons. you'll see it's roughly 45 degrees right here at the beginning, which means it's a 1 proton to 1 neutron ratio. But then you'll see if you just follow the black line, it starts to fall and starts to flatten out. What that shows is that as atoms get bigger, you need more neutrons in the nucleus than you have protons. And that has to do with the stability of the nucleus and nuclear physics that we're not going to get into right now. So we'll get back to this in a minute. I just wanted to introduce that chart. And I actually have a picture of this graph in my classroom. It's not quite as fancy as this, but it is a picture. We need to get back to the notes. All right, let's just go through some basics. Just like with organic chemistry, this is just an introduction to nuclear chemistry, and ultimately it would break down into nuclear physics. So radioactive decay, what this is you have a nucleus that is not stable. Things are not happy in the nucleus for a variety of reasons, and so what they do is they start flicking things out. 3 common things that you can, well, not you, but the nucleus can toss out are alpha particles, beta particles, and gamma. Now, gamma gets tricky. You can refer to it as a particle, or you can refer to it as energy or a wave. And this starts to get into the weird world of quantum mechanics and physics that we're not going to get into right now. So, an alpha particle is essentially the nucleus of a helium atom. Beta is essentially an electron. Now, it's more complicated than this, and I'll show you when we get to a practice example. And gamma is like this. Now, often in our examples, you're not even going to see the gamma because it's got a mass of 0 and an atomic number of 0. You don't even see it. This often happens alongside of other nuclear reactions. And that brings up another interesting thing. Until this lesson, we have never changed a nucleus. Everything we have done, we have combined atoms, we have separated atoms, we have rearranged atoms, but we've never changed a nucleus. So this is a very special area of both chemistry and physics and so on. So a common problem looks like this. You're given pieces of a nuclear reaction, and in this case, these are all radioactive decay, which is one type. And you have to figure out what's missing. So you just add up the top numbers and you add up the bottom numbers. And in this case, you would come up with a 0 and a -1. And that is a beta particle. Now, I've seen this written different ways. I've seen it written the way I did, 0, -1 with a little e. I've also seen 0, -1 with the beta symbol. Whatever works for you is good, as long as it accomplishes the idea here. And so this would be beta decay. Now, what's interesting here, and I mentioned that it's more complicated than just sending out an electron, is if you look at the numbers, 234 to 234, so the mass hasn't changed, at least not on a large scale. But look at the atomic number. It went from 90 to 91. The atomic number went up. So essentially what is happening here is a neutron is turning into a proton, which is why the atomic number would go up by 1, but the mass number stays the same. All right, next one. In this case, the only way to get 226 to add to 230 is 404. The only way to get an 88 to add to 90 is to add 2. And this ends up being a helium nucleus. This is called alpha. And there's my very poor drawing of an alpha symbol. And another practice problem right here. same idea, but in this case, you were told the alpha particle and you just have to figure out what the new isotope. In this case, we have radon-222 becoming polonium-218. Now back to half-life, we did this when we did rates and so on. Half-life, it says is usually first order. I actually don't think that's true. I think it's always first order. So I think we can just say half-life is first order. I mentioned this equation in which A sub 0 is the starting amount at time 0. A sub T is the amount of original substance that remains after time T. And in this equation, T can be any amount of time, but I also had taught you this shortcut. Now this shortcut over here only works for a first order scenario like half-life. And this allows you to convert between the actual half-life, the amount of time it takes to cut the amount of starting substance in half, and the constant here. So be careful. This shortcut equation, T1/2 is the half-life time only. Whereas over here, this T can be any amount of time, whether it's the half-life or something else. So I have a few examples. So let's take a look at this one. It's radon 222 has a half-life of 3.823 days. If we start with 10 grams of this isotope, how much is left after this many days? Now, there's a few ways to solve this. If you're in pre-calculus or calculus, you might know an equation that combines this into one problem, but I choose to do it the way we do it using the first order integrated rate law. And so I'm first going to take and cut something in half. So 2 divided by 1, that's cutting something in half. You can use whatever numbers you like, plug in the half-life, solve for K. And you can do it using this equation, you get this, or you can use the shortcut equation and get the same answer. Once you know your constant, plug it again into the first order integrated rate law, like here, and you can solve for A sub T, which is the amount of substance that remains. So we get 0.313. And again, that's how much remains. It's not how much has reacted and undergone this nuclear reaction. If you want to know that, you would subtract 0.313 from the starting amount of 10, and then you would be able to calculate how much actually reacted. Now, a second type of reaction is called a bombardment. It's a pretty cool name. And what this means is you take some sort of nucleus and you bombard it or hit it with something. You can hit it with tiny things like electrons or protons or neutrons, or you can hit it with larger things like other atoms. And right here, it says that it has to be a stable nucleus. I don't think you have to start with a stable nucleus, but that seems the easiest, and that's what we'll focus on. Now, you might say, why would we do this? Why would we take a stable atom, hit it with something else that might cause it to be radioactive? Well, this is very useful, especially in medicine, possibly in chemistry and physics and biology and earth science. I mean, really all sciences. And there are commercial applications as well for this technique. So I have a couple examples. Here I take a stable aluminum, hit it with a neutron. Notice the neutron has a mass of 1, but an atomic number of 0 because it has no protons. And in this case, we make a new isotope of aluminum, which is radioactive, which could be useful for a variety of things. Next one, calcium-48. We're going to crash this into a plutonium atom, which, funny enough, I don't think there's any stable isotopes of plutonium. And we would make a new isotope here, which is a fairly recent discovery, very large atom. And this right here shows that it's giving off 3 neutrons. Now, speaking of these symbols, I ask, what about this? What is 1 over 1? Well, if you think about it, 1 over 1, and what must be the particle? Well, it's got an atomic number of 1 and a mass of 1, so that is either known as a typical hydrogen atom, or you could say that it is simply just a proton. I also mentioned this one, and I don't want to spoil it. I'm going to let you think about this one. What might have an atomic number of 1, but a mass of 0? So let that one just simmer. Don't just look it up right away. Think about it. See if you can figure it out. Then look it up. More about isotopes. A very important technique is called mass spectroscopy. In other words, looking at the spectra of the mass of different isotopes. The machine is actually quite complicated, but the idea is summarized in this picture here. You send particles from here, and you send them through a magnetic field, and you keep adjusting the field until the particle makes it through this path. It wouldn't probably curve like I've drawn it, but it'll just keep going until it hits this detector like here. And you would try different magnetisms that you could measure. And when the particles hit the detector here, you would then take note of that. And you would get a spectrum like this. So this particular element was put through a mass spectrometer, and it gave off these isotopes. It gave off one with a mass of 92, 94, 95, 96, 97, 98, and 100. And then the height of each line here, 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 and here is how abundant it was. In other words, it looks like this isotope with a mass of 98 was the most popular and the one that was detected the most. If you wanted to find the average atomic mass or molar mass, if you use different units, you would just average all of these. What you would do is you would just take a relative height of every one of these peaks here, every single one. It doesn't look like a triangle. Actually, it did look like a triangle, should look like an arrow, and so forth, and you would see how they compare. A common question that comes up would be, what is the atomic mass of this element? And you might be told 90 and 92 and 96. 1, 2, 3, let's just go with that. And 100. And actually, let me put them in order. Let's do 98 and 100. You might be asked, which of these is the most likely atomic mass of this element? Well, it can't be 90. There's no isotopes at all. 92, well, there are some, but that's way at one extreme. So that's some of them, but that's not the average. 100, that's at the other extreme. So these are out so far. And then between 96 and 98, well, even though we have a lot of them at 98 right here, we only have a few above 98, which means it's probably not 98. So the best choice here would be 96. And so you might see a problem like that in the future and such. This stuff here and tidy up the screen. Now, another calculation you might be given is you might be told the percentages of these peaks. Now, this example I have is extremely simplified. It says calculate the atomic mass given the following isotopes of lead: lead 210, 209, and 207. And we've been told that the abundance is 9%, 5%, and 86%. Now, this is a oversimplified problem because it's assuming lead only has 3 isotopes. In reality, lead, I'll go back to this, has many isotopes. So I believe I can plug in lead here. So I told it to focus on lead, and you'll see that lead has many. Let me see if I can back out. No, I'm zooming in. Let me back out of this. These are all the isotopes of lead right there. How many of them are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 40, 41, 42, 43. Roughly 43 different isotopes of lead, of which these black squares are the ones that are stable, and the colored squares undergo a variety of different nuclear reactions as listed here, like alpha, beta, and some more exotic ones that I have not talked about. So this problem, again, is way simplified, focusing on just 3 isotopes. But I don't think we really want to deal with 40 isotopes in our calculation. It's not hard, it's just time consuming. So what you do here, let's jump out of the way, is turn your percents into a decimal, divide by 100, which I've done here, here, and here. Multiply that times the mass number, so times 210 here, 209 here, 207 here, and then add up your values. 1, 2, 3, add them up, and you get the average. And notice the average is closest to 207 because it's such an abundant isotope, but it's a little higher than 207 because of the 209 and the 210. This is what's called a weighted average. All right, next. Now, regarding whether the nucleus is stable or not, ultimately, if you really get down to nuclear physics and such, certain combos of protons and neutrons are stable, and other ones are radioactive, and so on. There's an interesting thing that happens, though, in all atoms called the mass defect. Every atom weighs less than it's supposed to weigh, hence the name mass defect. So let me just jump into this first example. Take lithium-6. So lithium-6. And because it's lithium, it also has to have 3 protons. So this means it has 3 protons and 3 neutrons. Go ahead and take a look at page 15 in our textbook. So I'd say go ahead and stop the video, get the book out right now, look on page 15, 515, and you will see a chart. I'll grab it too. What do they call this chart? Chart of nuclides or something like that. And it will show nuclear masses. It'll show some of the subatomic particles like an electron and a neutron and a proton. And then it will show a variety of different isotopes. So take a moment, pause the video, and just look at this and kind of see what you can figure out from that chart. And then come back. And assuming you've looked at it, if you look up the mass of a proton, I have that here, the mass of a neutron, I have that here. Well, there's, in this case, lithium-6, there are 3 of each. If you add it up, this is what the nucleus should weigh. But it doesn't weigh that. It's pretty weird. The nucleus of a lithium-6 atom actually weighs this. And you'll find that on the chart on page 515. This missing mass, if you calculate it right here, is what's called the mass defect. That's how much mass is missing from the nucleus. So of course, the obvious question is, why is mass missing? Well, mass has been converted into energy to hold the nucleus together. That energy is called, let's see, do I have it here? Right here, nuclear binding energy. So like the name says, it's the energy that binds the nucleus. And we can analyze this using the very famous equation from Einstein, E equals mc squared. Typically, you see this in a nuclear physics class, but we're going to be able to use it here. This is regarding what's known as the strong nuclear force, which holds the nucleus together. Without this, all those protons that are tightly packed in the nucleus would just fly apart. So there must be something there, and it comes from the nuclear binding energy, and that comes from this missing mass that has been turned into energy. Now we can do a calculation of this. If I take the missing mass, which was here, convert it to kilograms, which is the appropriate unit right now, and then multiply that by the speed of light, which is what c is, squared, you get this many joules of energy. If you convert that to kilojoules, you get a number like this. Now notice this number, 10 to the 9 kilojoules. We don't typically see numbers like that. When we look at highly exothermic reactions like the combustion of methane or the combustion of gasoline and so forth, we typically see numbers like 10 to the 3rd kilojoules. This is a massive number. And that's why you often will hear that nuclear processes are so energetic. It ultimately has to do with these huge amounts of energy involved in the nucleus. All right, speaking of some nuclear reactions, there are 2 other reactions we should cover. One is fission, one is fusion. Fission is splitting an atom. So this is where you might have heard the term splitting the atom. That is fission. Fusion is sticking atoms together. So fusing atoms. That's an easier way to remember it. And I have some examples listed here. A great one for fission is what is done in modern nuclear power plants. They take uranium-235, which is a big atom, of course. They encourage it or allow it to fission, and that gives you smaller atoms, in this case, barium-141, krypton-92, and a lot of energy, and that energy is ultimately used to produce power for us. Now, there's an interesting thing that you'll notice here. The reason the uranium-235 splits is because it gets hit with this neutron. But notice more neutrons are produced. Here I have 3 neutrons. For 1 neutron that goes in, 3 neutrons get produced. And this, you'll probably have heard of the term chain reaction. This is a chain reaction because the very thing that is causing the reaction is produced. And not only in this case is it produced, but it's produced in greater quantities, which uncontrolled would cause the reaction to go faster and faster and faster. Until you run out of uranium, of course. Once you run out of uranium, then this is done. Unless there's something new that you can do fission with. Now, fusion, a good example of fusion is the sun. So our star, the sun, and pretty much every star, to some extent, takes hydrogen, turns it into helium, and gives off a lot of energy. So this is like lots of energy. And that's pretty obvious. If you go stand outside during the day, you normally notice there's a lot of energy coming from the sun. And that's only the tiny amount of energy that reaches our planet. Most of it just goes out into outer space and we don't even notice it. And one of the things that's really interesting here is ultimately that's where we come from. So this is a good eggmobile moment with extra spice coming out of the eggmobile. It is understood that the atoms that make up the planet Earth and our bodies have come from a similar process. Things like hydrogen turned into helium by nuclear fusion in stars, and then ultimately helium gets turned into other things like carbon and iron and so on. And ultimately, if a star is big enough, it explodes in a supernova, and then you get all the other elements. So it's kind of wild to think this, but the atoms that are in your body and in the food you eat and pretty much everything you experience ultimately came from a star undergoing nuclear fusion. And in some case, the star exploding in a supernova. So to finish here, I want to finish with two amazing statistics. Our sun, which is considered a medium-sized star, it converts 600 million tons of hydrogen to helium every second. Now, a metric ton is 1,000 kilograms, which is a huge amount. And our sun converts 600 million tons of hydrogen to helium every second. And it's done it for a long time. And fortunately, is going to do it for a long time into the future. This amount is just absolutely amazing. And it kind of helps understand how big the sun is. And then regarding stars, I think this one is even more amazing. Last time I checked, and this was a couple of years ago, it was estimated that there are approximately this many stars in the universe, which funny enough is close to a mole. It is figured that that this number is too low, so it's probably more than a mole. And what's crazy is that it is estimated that there are more stars in the universe than there are grains of sand on the earth. And that's just pretty wild to think about. I'm not even sure we can comprehend this because we don't typically deal with numbers like this. And even though you've heard of the mole number, you don't really interact with it. It's not like you get out marbles and you count a mole's worth of marbles to really appreciate how big that number is. And please don't, because you wouldn't succeed. It's way too big of a number. So that's just pretty mind-boggling how many stars are out there. And just our one star is undergoing this crazy reaction called nuclear fusion. And that seems like a good time to finish. So I'll use the galaxy pin here, let me get the galaxy pin all big. We are done. Yes. And the galaxy pin helps finish us up.